Okay, hello, welcome to my channel. My name is Silo Anch. In this video, we're going to learn about the domain and range of functions. Okay, then we're going to go ahead to find the domain of sub-functions, and we're going to limit ourselves to real valued functions. That is, functions in which the codomain is a set of real numbers, or let's say a subset of real numbers. Okay, so we start off with the definition of a function, which we did in a previous video when we had to look at the difference between a function and a relation. So we said that given a mathematical function, so we already assume that if, which is what we use to denote the mathematical function, we already assume that it's already a function. In other words, that if you're given two sets, okay, this is set x and then set y, then for each x in x, that is for each element of the first set x, there is a corresponding element in the second set y, such that this equation holds, such that f of x is equal to y. Okay, so what this means is that when a function is evaluated at some value in the first set, the result is in the second set. So this entry, this value here is called the input. Okay, you can call it the independent variable, while the result you get from the second set is called the output, which we can call it the dependent variable, because the value of the result depends on the value of the values of the input. Okay, that's nice. Okay, so just as a way of illustrating using this, so if a function, this is the function f, okay, this is set x, and then this is set y. Good. Now the set x, which stores the input, for example, the little x in set x, that set, okay, that first set is called the domain. Meanwhile, the second set is called the codomain. Okay, so yeah, that means we should have an idea of what a domain is the first set, okay, given a function. Good. But that is not really going to be helpful when we want to learn how to find the domain of some functions. So we need some other explanation, which we're going to do as we proceed. Okay, so let's move on. Good. So here we're going to define what a domain is in a way that will be helpful, and also what a range is. So let me bring this thing down here. Okay, that's nice. Now, we have domain and range. So when we talk about the domain of a function, the domain is a set of every possible input. Very, very important there. That, in quote, every possible input. Okay, so we need to talk about what we mean by possible inputs. Then the range is a set of coming. Okay, so what about the range? Well, the range is the set of only every output. So we have two different concepts there. The domain is a set of every possible input, which we're going to discuss, while the range is the set of only every output. So we talked about the codomain, that the codomain is that y, which is the second set, is the codomain, and it stores the output of the function. But the range seems to be a special part, okay, that is like a subset of the codomain, because you said that a range is the set of only every output. So yeah, what that means is that if we use, let's say, r to denote, if we use the range, that means if the range is denoted by r, then r is a subset of the codomain. So the case of the range r, which I'm using r to denote here, the range stores only the outputs, okay, and it stores all of them, but only the outputs. So every element of the range is an output. That is, there is a certain input in the function that the value will give us an element in the range. But the codomain may have some other values that are not actually outputs. Good. So the codomain is more general. It's more like a bigger set that contains the range and also contains some other. For example, if you consider a set of real numbers as your codomain, okay, the outputs may only be integers. For example, if you have something like a list integer function, or also like something like that, a list integer function, the output will only be integers. But the real numbers, the set of real numbers, is also a good codomain for that, because the set of real numbers contains the set of integers, but it doesn't contain but it contains the set of integers, and it contains more than that. Anyway, So that's a little difference between, it's not a little difference, but that's the difference between a codomain and a range. Good. Okay, so let's come back to the possible, we've talked about possible input. So when we say an input is possible, when do we say that? Good. So let's think of f, which is the function, as a map from set x to set r, where x is the domain, and then r here, I'm using r here to be my codomain. Good. Then an x in this set, in this domain, an element of the domain is said to be a possible input if, when we evaluate the function at that element, we get a result which is a real number. That is, we get a result which belongs to this codomain. Such an input is said to be a possible input. That is to say, this thing x will not be a domain if there exists an element in there that is not an input. And what do we mean by an element is not an input? Well, if the result is not in the codomain. Good. So let's do some examples to explain that. Maybe let me just give you a very simple case. So this is what I mean. So if you have a function to be, let's say, 1 over whatever you put inside, it takes 1 over that. Good. What happens when x is 0? Well, the function is going to be, f of 0 is going to be 1 over 0, right? Yeah. So 1 over 0, that is, f of 0 is going to be 1 over 0, but 1 over 0 is not defined because, of course, that's 0. Okay, so that's what we mean. That's an example of an input that is not possible. Okay, because we cannot divide by 0. Good. But every other real number for 1 over x, every other real number will make sense. Okay, so we have two examples here. The first, okay, the question demands us to find every possible input of these two functions. So the first function there is f of x equals to, let me just put here our solution. So the first function is that we are given that the function f of x, okay, what it does is that when you give it anything, it will take the square of the thing, it will subtract 1 from the result, and then take the reciprocal of the result. That's what the function does. Good. So we want to find every possible input of this function. Okay, so let's see what we can do. Well, we're going to start off with a question. That's as a strategy. When would this function be a problem? Okay, when would this function have a problem? Yeah. So this function is a radical function. Sorry, it's a rational function. Yeah, and a rational function has problems where the denominator is 0. Okay, so good. So because this is a fraction, if the denominator is 0, is a big problem. So any input that makes the denominator to be 0 is not a possible input. So we should be looking out for that. Okay, and as a way, we're going to start off by saying that we should set the denominator to 0. When we set the denominator to 0, we're going to be able to get the value or values of x that will give us 0 in the denominator. In other words, those values are not possible inputs. So we solve for x from here. You add 1 to both sides. When we add 1 to both sides, we get x squared equals to 1, and then we take the positive or negative square root of both sides. That will mean that x will be positive or negative 1. Okay, that's nice. So these are the two values of x that will give us 0 in the denominator. In other words, that will give us problems. So what that means is that these two values are not possible inputs. So the possible input will be every other real number except these two values. Alright, good. So as a way, since we can't list, because the question says we should find every possible input. Since we can't list the possible inputs, we're just going to collect them into a set. And we're going to call that set the domain, because of course that's just the definition. It's a set that contains every possible input. So the domain of the function, so let me just say the domain of f is, so let's use the set builder method to collect them. So let's say every x in R, that is every real number x, such that such real numbers are not either 1 or negative 1. Good. So this is a way. We can also use the set an interval notation by saying, okay, let's remove 1 and negative 1 from the set of real numbers. And we can do that in this way using intervals. So this is a way we can do that. We take from negative infinity up to negative 1, but we don't want negative 1, so we use a parenthesis to show that we open it at negative 1. In other words, negative 1 is not included. Also, between -1 and 1, there are also other real numbers. So we take from real numbers between -1 and 1, but -1 and 1 excluded. That's why we're using the parentheses. And then lastly, from 1 up to infinity. Good. By neglecting, removing the 1, removing the -1. So this is also a way to represent it. These are interval notation. This is a set builders method, interval notation. Okay, that's it. Let's do the second one. So for the second one, we have g of x equals to, this is it. We have g of x equals to the square root of 4 minus x squared. So let me put it down here. So we have the second function, g of x is equal to the square root of 4 minus x squared. Good. So you want to find every possible input of that function. So let's see. Okay, so let's see what we can do. So a similar thing, we're going to think about this function. When will this function be undefined? When will it have a problem? Okay, so this is square root function. Well, square roots are undefined for negative inputs. All right, when we have a square root, we want the radicand to be non-negative. Good. So that's what we're going to start off with. We're going to start off by saying that we should set the radicand, which is 4 minus x squared, as non-negative rather. That is 4 minus x should be greater than or equal to 0. So here we're going to find the value or values of x that will make this inequality true. Good. Very, very important there. So what can we do? Well, it's a strategy, which is the right thing to do. We'll start off by factorizing the left-hand side. So let me just do the factorization. And I'm going to use the fact that when we have difference of 2 squared, for example, that is a squared plus b squared, we can factorize that as a plus b times a minus b. Good. So where 4 can be written as 2 squared, and then x squared is already there. So that has this the two numbers, or the 2 squared and x squared have the form, so we can make use of this. All right. So I'm going to write it as 2 plus x times 2 minus x. Sorry, 2. Where is that? 2 minus x, okay, good, is greater than or equal to 0. That's just by factorization. We can use the factorization method as well. Okay, that's nice. Then the next thing is to consider what we call salient point. That is the endpoint of an interval. Okay, so since this is greater than or equal to 0, an inequality, we're just going to start off by saying we assume that this is equal to 0 instead. Okay, it's not actually equal to 0, but you just think of it as being equal to 0. So since the product of two things gives us 0, it means at least one of them must be 0. That is, it's either this bracket is 0 or this other bracket is 0. But if the two brackets are 0 for each of them, for the first bracket, if 2 plus x is 0, it means that x is the same thing as minus 2. And also, if 2 minus x is 0, it means that 2 and x are the same. That is, 2 is the same thing as x, or x is the same thing as 2. Okay, so these two values that we get by setting this inequality equals to 0, that is as an equation, those two values will give us the extreme points or the salient points of our interval of solution. Good, so this is what we're going to do. We're going to use the 2 points to partition the real line. So I'm going to start off from negative infinity up to positive infinity, so negative infinity to positive infinity. Okay, then we know that between 2 and minus 2 lies on the left hand side of 2. That's how I'm going to write it. Okay, so we've partitioned the real line into 3 intervals. Maybe let's give the intervals names. Let's call this interval A, interval B, interval C. Good. So we're going to test for each of these intervals which of them will satisfy the inequality. Okay, good. So let's see what we do. Well, I'm going to start off with, before I go to the intervals, I'm going to start off with this point, the minus 2 and the 2. Do they satisfy this inequality? This is the inequality we're considering. So you look at when x is minus 2, what happens? So 4 minus 2 for x, and then x has been squared. But minus 2 squared is 4, so that's 4 minus 4, but that is equal to 0. So the left hand side is 0. Sorry. The left hand side is 0 when x is minus 2, but 0 is greater than or equal to 0. That's true because 0 is equal to 0. One of the conditions is satisfied. So minus 2 works. Then look out for 2. When x is 2, what happens? So you plug in 2 for x, that's 4 minus 2 in place of x, and then you square that. But that's the same thing as 0 because 2 squared is 4, which means 2 also satisfies. Good. So we are now going to go over to the interval a. Well, the interval a is from minus infinity to minus 2. So you pick a number from there. For example, you can pick minus 3. Put minus 3 into the inequality that we started with, that is into the main inequality, and then see what happens. Good. So that means we're going to have 4 minus, in place of x we put minus 3, and x has been squared, we square that, but that is going to be the same thing as 4 minus 9, which is negative 5. But negative 5 is less than 0, which fails to satisfy that inequality we started with. So that means interval a fails. We go to interval b, which is from minus 2 to 2. Maybe let's pick 0. So we put in 0 into the function, into the inequality, that will be 4 minus 0 squared, but 4 minus 0 squared, but 0 squared is 0, which gives us 4, which is greater than 0. And that satisfies the inequality. So yeah, B satisfies. We go to the third interval, which is from 2 to infinity. Maybe we can pick 3, you can pick 5, whatever you like. Maybe let's pick 10. But it doesn't matter even if we pick any number greater than 0, it doesn't have to be a whole number anyway. So this is 4 minus, we pick 10 squared, but 10 squared is 100. Even if we pick 3 squared, it will be 9, which leaves us with a negative number, that is, it less than 0. And that fails to satisfy this inequality, so that fails. Which means the only interval that satisfies is the interval b, together with the minus 2 and the 2. So this is what we're going to do. Okay, so we're going to go ahead and use those the interval. So I'm going to write it out here, that the domain of the function is going to be, now it's going to be the interval from minus 2 to 2. But remember, minus 2 and 2 also satisfy. So we're going to stay from minus 2 to 2. And here I'm using a squared bracket. That is to show that the silent points minus 2 and 2 are included. Alright. Before the previous example, I used open bracket for minus 1 and 1 because those points were not included. But here minus 2 and 2 are included. So we use the squared bracket to denote that. Okay, so this is the domain. Or remember, you can use set builder method to say that the domain is a set of real numbers x, that is x in R, such that, let me write the R well. Set of real numbers, you have to respect it, okay? It contains a lot, okay? Such that x lies between negative 2 and 2, with negative 2 and 2 included. So I'm using the less than or equal to sign, not just a strict inequality. Okay, so that's a way to represent the domain. That's how to find the domain of functions. So you can look back at that anyway. Good. These are just two functions. There are very many of them. And it will just depend on when the function is defined. For example, the logarithm function, the inputs, okay, or the entries of a logarithm must be positive for the logarithm to exist. All right, good. So you also think about that as well. So yeah, that is a way, that's a strategy you can make use of in finding the domain. But actually here we haven't tried to find, maybe, or do an example on finding the range of a function, and that is because to find the range of a function, we will need some other tools to work with, and maybe some other conditions as well, which we'll do in our subsequent videos anyway. Okay, thanks for watching. Please share this video with your friends. If you have any question, put it in the comment section. Please subscribe to my channel. We'll continue from my next video.